to a brand new video on the CAMP signaling system. And what we're going to do in this video is first discuss the difference between a first and second messenger. Then we wanted to look at the process of the CAMP signaling system from beginning to end and how that happens. So then we will actually discuss how we can turn that off. So what we want to start off with is simply looking at the overall differences between how cells that have that are responding when they respond to a hydrophobic or a hydrophilic hormone. So we'll first do hydrophilic. Remind yourself that hydrophilic means water loving, and then we'll look at hydrophobic. Hydrophobic meaning water fearing. So hydrophilic hormones, that hormone will be water loving. It means it dissolves in water. It has a charge to it. Or polar, so it could be ionic or polar compound. When it travels through the bloodstream, it travels in the water's fluid. It can interact with it. So when it wants to impact this cell here, it will have a receptor on the outside of the cell. An extracellular receptor would be present. And in order for this, once it binds to do something, it needs something on the inside of the cell to give a response. And that's going to be a G protein. Now, G proteins, these are going to be numerous, and there's many of them. A good way to think of G proteins is, let's imagine that you are the hormone and you have snuck out of the house to go to a concert that your parents wouldn't let you go to as a kid. And now you got to sneak back in to try to not get caught. So you climb up to your bedroom window and your little brother or little sister's in there. So you knock on the window when you bind to the receptor, and little brother, little sister is inside there, and that's our G protein. And depending upon what kind of little brother, little sister you have, will depend upon what happens next. It could be a cool little brother, little sister who decides to let you in, you don't get caught, you get away with it, and nobody knows. Or he could be, or she could be a very mean little brother, little sister, and decide to tell on you, or even leave you outside in the cold. So depending upon the G protein, when it is activated, will lead to the activation and use of what is called second messengers, a second messenger system. So this makes our hormone the first messenger. So a big part of why this has to happen, if you are a hydrophilic substance, if we were to zoom in on the cell membrane, remember we are going to see a bunch of phospholipids. And these phospholipids are mostly going to have these fatty acid tails of that, these two fatty acid tails, these diglycerides, and this major lipid component that is there will not allow a hydrophilic charged substance to cross it. So it must use something from the inside. It must use a G protein, which will activate second messengers. Now, on the other hand, hydrophobic, which is water insoluble, which is nonpolar covalent bonds producing that. Let's use a great example of a steroid hormone. And so if I had steroid hormones, this steroid hormone here, let's say this is testosterone, estrogen, whatever we want to use there, has 4 fused rings, 3 6-carbon rings, 1 5-carbon ring, and this being hydrophobic is water insoluble but is lipid soluble. So when it passes through the cell membrane, it can go right through the phospholipid bilayer. Well, big part of the problem is here though is since it is not water soluble, it must travel through the bloodstream on a transport protein bound to something like an albumin, a transthyretin molecule, something like that. Okay, so when it comes into the cell, as it enters, there will be some organelles inside the cell. In this case, let's say the mitochondria, but this can happen on the nucleus or any other cell organelle. And that this organelle will have a receptor on it And when this receptor on the inside of the cell, an intracellular receptor, is bound to, this can actually cause this organelle to do something like make ATP. And this is why we can see that steroids will give energy to people. So we will notice that the cell's response occurs inside the cell on an organelle with an intracellular receptor. So very dramatically different versions of action depending upon the hormone, which is very important to understand in the world of pharmacology as well. So let's take a look at hydrophilic hormone and how it might work with a second messenger. Of the most important second messenger we're going to talk about is cAMP. So we're going to draw a cell here. And on this cell, we need to add a receptor on it, an extracellular receptor. And let's use norepinephrine as our example here. Norepinephrine, being an amino acid, catecholamine, is a water-soluble hydrophilic hormone. And when it binds to the receptor, let's say an alpha-1 receptor, when it binds to it, it will cause a change in shape. Now, this being a hydrophilic hormone, must be linked to a G protein, and there are many G proteins out there. But when G proteins are activated, they can release a cascade of events. So the binding of the hormone to the receptor site changes its shape, which will then activate that G protein. Now, in the cAMP signaling system, G protein activates an enzyme complex called adenylate cyclase, abbreviated here AC. Adenylate cyclase converts ATP, adenosine triphosphate, and converts it to cyclic adenosine monophosphate, or cAMP. Now, also pay attention that it will give up two inorganic phosphates in this chemical reaction to go from triphosphate to monophosphate. So those phosphates will come in handy in a moment. Now, cAMP activates something called protein kinase, and all a kinase is an enzyme who can transfer these phosphates to something and phosphorylate them to make them do something. It is going to transfer this energy, the potential energy that was in ATP, to something to get something done. Now, protein kinase can send this over to some enzyme complexes. So we can take some enzymes and turn the enzymes on or off. And we might be able to adjust chemical reactions in the cell. Synthetic enzymes, enzymes used in digestive processes, enzymes used in a variety of other functions. So also, we will go in and we can open up a type of protein that lets calcium come in. So a calcium channel could let the calcium cations enter this cell and cause a muscle contraction if this was a smooth muscle, or cause exocytosis if this was another endocrine cell. So it can cause smooth muscle contractions, cardiac muscle contractions, exocytosis of materials. So a wide variety of impact due to these two functions of turning on enzymes and calcium. Now, to turn this off, we use a very simple enzyme. We use an enzyme abbreviated PDE. It stands for phosphodiesterase, and phosphodiesterase will come into cAMP and deactivate it. And when we do that, we could shut off protein kinase, stop the enzyme actions, shut the calcium channels off, and turn off this cell's response. Now, for example, cAMP was causing calcium to come in, causing a muscle cell to contract, like heart muscle cell. If we used a PDE inhibitor and we prevented this from happening, the heart would be able to contract more forcefully. So we use these classes of drugs to help people's hearts as a positive inotropic. So I hope you find this video helpful to understand this process, and we could use it in some other drugs and take a look at it with some pharmacology videos as a basis. But this concludes my video on the cAMP signaling pathway. I hope you find it helpful. Please don't forget to comment and let me know what you would like to see me do in future videos. Leave a like rating. I'd always appreciate that. Thank you so much for watching.